All right. Hi, everyone. My name is Brandon, and today we're going to do multivariate time series clustering of US states using COVID-19 data. Here is our roadmap for today. We're going to start off with a brief introduction. Then I will introduce you to the data set. After that, we'll do a couple of steps before we cluster the data, and that will be cleaning the data, smoothing the data, and scaling the data. After that, we'll move into clustering, and then we'll wrap everything up with a conclusion. So for our introduction, I just want to break down what I mean by multivariate time series clustering of US states using COVID-19 data. And specifically what I mean is that we will use hierarchical clustering to group US states based on multiple COVID-related epidemiological variables per day. And our goal after our cleaning, pre-processing, and clustering is to take those clusters and turn them into a map, something that looks like this, and see if we can identify any patterns. Now I'm going to introduce you to the data set. Our data comes from the COVID-19 Data Hub, which provides daily summaries of epidemiological data, policy measures, mobility data, and geospatial identifiers from government sources around the world. In R, we can access this data by using the COVID-19 function from the COVID-19 library. And here you can see that with the parameters country equals US and level equals 2, when we run this, we can query all of the data for the United States at the state level. Here we can see that there's around 77,000 rows, each of which correspond to a state and a day, and 47 variables. Now, we're not interested in all 47 of these variables, and we're really only interested in a couple of the epidemiological variables, which I have defined here. So I think that most of these are pretty self-explanatory, but I'm going to point out now that these first 7, confirmed, deaths, recovered, tests, vaccines, people vaccinated, and people fully vaccinated, are cumulative variables up to that date. And hospitalizations, ICU, and ventilators placed are just the absolute value that happened on that day. And that's something that we'll deal with a little bit later during cleaning. Also, before we start cleaning, I just want to break down a couple of how many missing values there are for each variable. So you can see in this code here, we're going to take our data and we're just going to filter it down for the data that we're interested in, which is just looking at the 50 states and also looking at all of the data for 2021 and 2022. Then we will select our variables of interest, which are the epidemiological variables, and we will summarize them by taking the sum of the missing values and then rearrange that into an easier to understand format. So we go ahead and run this, and we can see that what we're left with here is this data frame, and we can see that there are a ton of missing values in the recovered and the vent variables. I know that just from playing with the data in this subset that this is around 95% missing values. So for that reason, we'll have to exclude these 2 values from the analysis. And the only other variable with missing values is this tests variable. And there are only 2, and again, we'll deal with these during cleaning. Speaking of which, let's start cleaning our data up. So the first thing that we'll do is we'll load our data in. We've already seen that. And we have 77,000 rows, 47 columns. So let's start by trimming down the columns. What we'll do is we will select our columns of interest, and you'll see that this 47 columns will jump down to 8 columns. The columns that we'll be working with today are the date, the administrative area level 2, and then the confirmed deaths, tests, vaccines, hospitalizations, and ICU. The next thing that we want to do is we want to cut down this number of rows. And the way that we'll do that is we will just filter our data by the administrative area level 2 in the 50 states. And I think it's important just to note that this means that we will be excluding areas like Puerto Rico, Washington, D.C., and the Northern Mariana Islands. And we will also filter our data to only include the data that falls in 2021 or 2022, which is the 2 full years of data that are encapsulated in this data set. So we'll go ahead and we'll run that. And you can see that we are left with 36,000 500 rows. And this makes sense for 365 days per year over 2 years for 50 states, which is just a nice confirmation that we do have the right number of rows. The next thing that I want to do here is just arrange the data. This step is not necessary, but I thought it would be nice for this presentation because it makes the data a little bit easier to follow along with. So I've gone ahead and sorted the data by the date and the state, and we can see that arrangement here. The next thing that we want to do is handle those 2 missing values that we identified earlier. So what we'll do is we'll subset our data by those rows that do not contain a complete case. And when we run that, we can see those 2 missing values right here. They're in the tests column, and they occurred on April the 5th and April the 6th, 2021 in Ohio. If you remember, the tests column is one of those cumulative columns. So a really nice way that we can deal with these missing values is by doing a linear interpolation. The way that we do this in R is pretty easy. So what we'll do is we will group by the state because we're only interested in Ohio. And then we will mutate the tests column using this NA_approx function, which does the linear interpolation. And when we run this, you can see that it fills in those missing values with these 2 numbers here, which seem to make sense for this data. The next thing that we want to do is transform our cumulative variables. So let's call back all of our data here. And if you remember, these first 4 columns are cumulative, and these last 2 here are by per day. And what we want to do is convert all of our columns into per day data so that it's easier to compare across variables. The way that we do this in R is pretty easy. Again, we will group by the state, and then we will mutate our 4 cumulative features by taking the number for each observation and subtracting it by the previous observation. And by doing that, what we'll do is we'll take the cumulative values, and we'll see these 4 columns here will get much smaller, and these 2 will remain the same, and convert them into daily values. So now all of our features are in per day. So that's all the cleaning steps that we're going to take, and I thought it'd be nice to take just a second to look at the progress that we've made so far. So in this picture, what I've done is I've selected 4 representative states, California, Michigan, New York, and Texas, as representative states for the West, Midwest, Northeast, and South. And we can see the data for these states, for these time series, plotted here. Looking at this figure, 3 things stick out to me immediately. The first thing is that the data is very jagged, and this is going to pose a problem for our clustering. If you remember, we're going to be doing hierarchical clustering. So the first step in that is taking the distances between our time series. And when the data is really jagged like that, that could be bad for finding those distances. The next thing that I notice is that the scaling within each variable is off. So California is always on top, and Michigan is always on the bottom. And this is simply because the population in California is way higher than the population in Michigan. So in the pre-processing, we're going to have to make sure to scale within the variables so that population doesn't bias our clustering results. The other thing that I notice is that the scaling between the variables is also off. And we can see that, for example, the tests and vaccines, these are much greater than the deaths and hospitalizations. And again, this is something else that we'll have to scale so that these, these larger features don't dominate the clustering. So let's move on to our pre-processing. The first thing that we want to do is smooth out our data so that we can make those distance calculations a lot cleaner. And for this, I tried 2 different smoothing methods. The first one that I did was the 7-day average, which just averages the data over a week. And the way that we can do this in R is pretty easy. So we have our clean data here. What we'll do is we'll group by state, and then we will mutate our features by taking a rolling mean of those features for 7 days. And when we do this, we'll just see a small change in all these numbers here. And when we plot this, we can see that this is much smoother than before, but still has a lot of jagged edges in it. And I think this would actually be fine for the clustering, but I wasn't super happy with this result. So I tried another clustering. Specifically, I tried the low S clustering. This is locally estimated scatter plot smoothing. And what this does is it employs a local polynomial regression to fit small parts of the data more accurately. And just like before, this is pretty easy to use, but instead of mutating our features by doing a rolling mean, we'll just mutate our features by doing the low S. So let's go ahead and run that. We can see a small change in our numbers. And when we take a look at these plots, we can see that these are much smoother than the 7-day average. And I've gone ahead and plotted all three of these so that we can directly compare them. So very jagged when we just had our raw clean data. And then we have the 7-day average, which is a little bit jagged. And then we have our low S, which is mostly smooth. And in general, I think that the low S is superior to the 7-day average in terms of preserving the original trends over time without over smoothing the data. So this is the smoothing method that we will use. The next thing that we want to do in pre-processing is we want to scale the data. This is very straightforward. We just group by the state, and then we will scale all of our features using the scale function, which just means that for each group, we will subtract each value by the mean of that group and divide by the standard deviation of that group. After we do the scaling, we can go ahead and plot this. And now you can see our data at the end of the pre-processing. So this is the last pre-processing step that we're going to do. And what we can see is that after the smoothing and the scaling, everything looks really good. And also both within each variable and also between the variables, these curves are a lot more comparable. And so the application of both smoothing and scaling ensures that the time series data can be compared equitably both within and between the different variables. And this is going to be very important for when we do our clustering. So let's take a look at our clustering. So for the clustering, really the most important part for us is going to be this distance calculation. So let me walk through how we calculate the distances for this multivariate time series data. And really the bulk of it is in this for loop right here. So let's take a look at this for loop. So for each feature, what we're going to do is we are going to select one of our features. So let's go ahead and select the vaccines feature. And we're going to rearrange this data into a form that's a little bit easier for us to use for taking distances. That's what these next 3 lines here are going to do. So let's run those. And you can see our rearranged data is now arranged in a way so that each row is a state, and we have 50 states, and each column is a date. And there's 730 of those, makes sense, 365 days per year for 2 years. So this would be January 1st, January 2nd, January 3rd, and so on. And now what we want to do is we want to calculate the distance matrix between all of these states. So let's pass this into our dist function. And so the way that this is working exactly is that you can imagine, for example, if we wanted to take the distance between New York and Texas, what we would do is that for each day, we would take the distance between these 2 time series. And then in this case, we're just using the Euclidean distance. So we would take this squared plus this squared plus this squared and so on. And then we would take the square root of that. And that would be our single number distance between New York and Texas, specifically for the vaccines feature. So we can repeat that process for every single state for the vaccines. And you can see that we end up with this 50 by 50 distance matrix. Now we're going to repeat that process for all of our features. And then we'll be left with these 6 distance matrices. And because of our pre-processing, what we can do here is we can actually aggregate these 6 individual distance matrices into a single overall distance matrix. And that's going to look something like this. And now once we have our overall distance matrix, we can pass that into the rest of our hierarchical clustering algorithm in order to get a dendrogram. So I've gone ahead and done that, and here's the resulting dendrogram. And here it is zoomed in, so it's a little easier to see. And this is great. And now the next thing that we're going to be interested in is figuring out what the optimal number of clusters is so that we can figure out where to cut this dendrogram. Something that I want to do really quick, just so that we can take a look at what we've done so far, is take a look at this small cluster right here, this Georgia-Texas cluster. I think this is the most similar two states here. And if we take a look at the scaled data for these two states, Georgia and Texas, we can see that the trends here are actually very similar, which is a nice visual confirmation that our clustering is working correctly. I've also gone ahead and plotted the unscaled, the unprocessed data for Georgia and Texas, just so that we can see that, like, these trends may be noticeable a little bit by the naked eye here, but this is something that would be pretty hard to do without doing all of the processing and clustering that we've done so far. So let's take a look at finding the optimal number of clusters. And the way that we're going to do this is by looking at the gap statistic. So the gap statistic compares the within cluster variation with the expected variation under a reference null distribution, which we generate using bootstrapping. And this is a very fancy way of saying that we take a look at the gap statistic, and the greater the gap, the more distinct the clustering is from being totally random. So what we can do is we can pass our final distance matrix as well as our clustering function into the clusgap function in order to create this nice chart that plots the gap statistic for a various number of clusters. And, And the way that we can use this chart to determine the number of clusters, there's a couple of different ways, but the way that I decided to do it for this analysis is by using the first standard error max method. And the way that this works is by identifying the smallest number of clusters whose gap statistic lies within one standard error of the first local maximum. So the first local maximum is here at k equals 7 clusters. And what we'll do is we'll just work backwards until we hit the last cluster that is inside of one standard error of this. And that would be right here at k equals 4 clusters. So this is our optimal number. Now that we have our optimal number of clusters, what we can do is we can cut our dendrogram at k equals 4 clusters. And you can see that zoomed in here. And now what we want to do, and this is going to be our last step, is we're going to take the clusters that we get by cutting our dendrogram at the optimal number of clusters and superimposing this data on a map of the United States. And that's what this last line is doing here. So we're just getting our map data from the maps package, and then we're creating a plot where we're plotting the states, and then we're filling in the states with the cluster data that we just found. So let's go ahead and run that. And this is our final result. So let's zoom in on this a little bit. And what this map highlights are a couple of regional trends within the COVID-19 data. So we have this substantial cluster here in the south that extends out to the west as well as another significant cluster that spans the Midwest and reaches into the Northeast as well as the Southwest, indicating some regional similarities in pandemic patterns. Moreover, there is one small cluster here in the Northwest. Also, Alaska is a part of this small cluster here. And there is another distinct non-contiguous cluster that comprises several northeastern states, as well as Illinois and California, which reflect some of the diverse responses and outcomes to the pandemic. And that's everything that I have time for today. So in conclusion, I just want to say that in this analysis, we used hierarchical clustering on multivariate time series data of COVID-19 metrics to uncover distinct regional patterns of the pandemic's impact throughout the United States. Our methodical approach, which included data cleaning, pre-processing, and employing the gap statistic to determine the optimal number of clusters, led to the identification of pronounced clusters in the South and the Midwest, as well as some smaller clusters in the Northwest and a distinct clustering that included several states in the northeastern United States, as well as Illinois and California. And these results offer critical insights for shaping targeted public health policies and underscore the pivotal role of data-driven analysis in comprehending and addressing the challenges of the pandemic. And that's everything that I have time for today. Here are my references for this presentation, and thank you so much for listening.